Hey, good afternoon. So today I'll continue chapter 4, which is mostly about the structure of the atom. If you remember last time, we talked about the Rutherford scattering. Rutherford scattering. And the Rutherford scattering has proven that atom has a positive charge concentrated in the center of the atom. Okay, so this means that there is a positive charge at the center of the atom. And we also know that John Thomson has discovered the electron, which is a negative charge, and that both of them give a neutral charge to the atom. So what happens next is, now let's take the hydrogen atom, which is the simplest atom. We know that the hydrogen atom has one electron and one proton. Of course, at that time, the proton did not exist yet, but at least we know, or we knew at that time, since the atom is a neutral, and since we know that there is one electron inside, so there must be something at the center that is a positive charge, and it has the same charge as the electron, but in a positive charge. So then they started looking at an atomic model, and the first model is what we call the classical atomic model. Classical atomic model, or classical model of the atom. So what is this classical atomic model? Is the following. We take the hydrogen atom. We know that there is a charge at the center, and there is an electron. And this electron is moving around the proton, or the positive charge. And we know that this electron is subject to a force, an electrical force. So electrical force in magnitude is equal to E squared 4 pi epsilon 0, and then 1 over r squared. This is the magnitude, of course, the magnitude of the electric force. And we know that we can apply second law of Newton, which is the force is equal to the mass times the radial acceleration, because the electron, since there is no external force except the electric force, which is constant, so the electron will be moving with a constant speed, which means in a circular motion, the tangential acceleration will be 0, and the radial acceleration will be equal to the speed of the electron divided by the radius. The radius is the distance between the positive charge and the electron. So this gives us that the mass times the radial acceleration divided by r is equal to the force, which is E squared over 4 pi epsilon 0 r squared. Well, we can easily see that the velocity is equal to the absolute value of the charge of the electron divided by 4 pi epsilon 0, the mass of the electron, and the radius, or the distance between the electron and proton. Right? Now, let's talk about the energy of the system. We know that the energy is equal to the kinetic, the total energy of the system is equal to the kinetic energy plus the potential energy. Of course, here we have an electrical potential energy. So the kinetic energy is 1/2 in v squared. So we'll see after calculation that the velocity of the electron in the atom is so small that we apply classical physics, which means the classical formula or classical form of the kinetic energy. So the kinetic energy is equal to 1/2 in v squared, which is equal to 1/2 m, and v squared is given by this, so it will be E squared over 4 pi epsilon 0 m r. This goes, it will give an E squared over 8 pi epsilon 0 r. So this is the kinetic energy. Now, what about the potential energy? Well, the potential energy, the electrical potential energy between two charges. So this is the kinetic energy, and now the electric potential energy is equal. If you remember, the potential energy between two charges. Okay, so let me just 1 second. Okay, so the electric energy, potential energy between two charges, let's say Q1, Q2 over 4 pi epsilon 0, and R12 is the distance between the two charges. So here we are talking about the value of the charge. Okay, we know that the electron has a negative charge, which is minus E, and the proton or the positive charge is a E, so it is E squared divided by 4 pi epsilon 0 R. This is the potential energy. Now, if we look at the total energy will be equal to the kinetic energy, which we already calculated, 8 pi epsilon 0 R, minus the potential energy, which is 4 pi epsilon 0 R. Yes. And this means that the total energy is equal to minus E squared over 4 pi epsilon 0 R, which is negative. This is because the total energy is negative. This means it's a bound system. Okay, so this is the total energy. So this is the model of classical model of electron. The electron proton inside the hydrogen atom. Okay. Now, what is the problem with this classical model? Classical model, which the one that we just did, tells us that the energy of the system is minus E squared over 8 pi epsilon 0 R. And in fact, it has an issue that we have seen this in physics 207 in electricity and magnetism. This is a positive charge, and this is the electron. According to this classical model, the electron is moving with a velocity v. Now, we know that when a charged particle is moving, this charged particle is moving in a circular motion. This is circular motion. This particle will radiate energy. Okay, will radiate energy, radiate photons. Okay, so this means this particle will lose energy continuously. If this particle lose energy, what happens is this particle will continue to lose energy and until it will crash onto the nucleus. So this is a problem. So the classical model of atom has this problem that when a particle is moving in circular motion, it will radiate energy, which means it will lose energy. When it loses energy, it starts approaching, because it's losing the potential energy also, so it starts approaching the nucleus until it collapses with the nucleus, and there will be no atom. So here, there is a problem with the classical motion or classical treatment. Okay. So then Niels Bohr, which is a Danish scientist, a very, very famous scientist, one of the fathers of quantum mechanics, Niels Bohr, he came up with the Bohr's model of the atom. Of the hydrogen atom. And in fact, he was really impressed by Planck's work. So what the first thing is that he was impressed by Planck's work. If you remember, Planck told us that the energy of a photon or the radiation is absorbed and emitted in chunks, in packet of energy, and each packet or each photon or quantum has an energy that is equal to the Planck's constant times the frequency. So this is one time. So Planck's work that solved, if you remember, solved the problem of a black-bodied radiation. Okay. He was also impressed by the way Einstein solved the issue of the photoelectric effect. If you remember, the photoelectric effect. So the photoelectric effect tells us that when you shine photons or a light, a specific light on a metal, under a certain threshold, this light will extract electrons from that metal. And the energy of that light is used first to break the bond between the electron and the nucleus. So this is the work function. And the remaining energy is communicated to the electrons as kinetic energy. Okay. So, and if you remember, all this led to what we call quantization. Quantization means everything is has a specific quantity, like the charge of the electron has a specific quantity, the mass of the electron has a specific quantity. It's not a continuous quantity. And even the light is composed of quanta, and each quanta has a specific value. So this is quantization. So he believed in this quantization, and what he did, he applied quantization to the model, or to the atom, to the hydrogen atom. Now, he applied this quantization by making 4 assumptions, and I will explain those assumptions right now. So the Bohr assumptions. The first one is, in order to solve the problem of radiation that is lost when the electron is moving, he said, this is an assumption, by the way, there exist, so there are what he called stationary state or places in the atom, in the atoms, where the electron does not radiate energy or photons. Okay, so this is one thing. Okay. This is the first assumption. So this means that the first assumption, according to him, if we take, this is the proton, there are some states inside the atom in the empty space. If the electron is here and it is going or it is moving in those specific states, though the electron will not lose energy, will not radiate. So this is an assumption. The second one, the emission and absorption of energy by the atom, can only occur between or in transitions between those states. In transitions or in transitions between those states. So the electron, so what does this mean? The electron can jump from here to here or can jump from here to here. And this absorption and emission can only happen when the electron jumps between those states. Okay. The third assumption, well, actually, let me also do something here. He also said that each state or orbit has an energy, and when the electron jumps from one state to another state, let's say the electron jumps from let's say I have this is a positive charge, this is the negative, this is those are the orbiting, and for example, if the electron jumps from this state, I will call it initial state, to a final state. Okay, so the energy absorbed or emitted is equal, the energy absorbed or emitted during this transition is equal to the final minus the initial energy. Okay, we will calculate this energy later. So let me summarize. The assumption, the first assumption is that each the electron or the atom has a stationary state. When the electron is moving, occupying the stationary state, the electron does not radiate energy. The second, the electron can jump from one state to another state. When it jumps, depending whether it goes to a higher state or a lower state, there will be emission or absorption of energy by the atom. And this absorption or emission is just equal to the difference in energy between the two states. Okay, so this is the second assumption. The third assumption is that when the electron, let's say again, this is a final state, or this is the initial state, and this is the final state. When the electron moves from here to here, or from here to here, the electron is not in a free fall. We cannot apply classical free fall motion. Okay, classical the laws, classical laws or classical physics, laws of motion, do not apply during the transition. Okay, so in other words, when the electron goes from here to here or from here to here, it's neither in a free fall nor in under gravitation force. And the last one, now the last one is somehow complicated, but the easiest part of it is that the angular momentum of the electron, L, which is equal to the mass of the electron, the radius, the distance between the center of charge, positive charge, and the place of the electron, times the velocity, is quantized, is quantized, which means it cannot take any value. And in fact, he determined this value, L is equal to MRV. It is equal to an integer number, n, times a value that is called h bar. So n is an integer that goes from 0 until infinity, so it's an integer. And h bar is just the Planck's constant divided by 2 pi, a reduced Planck's constant. Okay? Please remember those 4 assumptions, because those are very important. Now, yes, you can tell, okay, it's an assumption, or those are 4 assumptions, but you will see that those 4 assumptions were one of the most important assumptions that Bohr did, and that led to quantum mechanics. So let's see what are the implications of those assumptions. Well, the first thing, let's start by the 4th one. We know that the angular momentum is equal to the mass, the distance, and the velocity. Again, let me explain. This is the proton, or the positive charge, and we have a particle that is rotating. This is the electron, and this electron is going with the velocity v, and there is a radius r. The electron has an angular momentum, okay, and this angular momentum, we know that angular momentum is equal to r cross vm, but because here in this specific situation r is perpendicular to v, the magnitude will be mrv, sine of the angle, which is sine of 90 degrees, and this is equal to 1. That's why. Okay, so mrv, this we know, but what is new is the quantization condition. Please remember this. This is the quantization condition. This is quantization, or Bohr's quantization condition, because this is a new. This is what Bohr is assuming, that the angular momentum is quantized. Now, let's see what is the implication of this. This means that the velocity of the electron is equal to nh bar divided by the mass times the radius. Now, we know that the velocity, we already calculated this from the classical model. The velocity of the electron is equal to E squared, or V squared, is equal to 4 pi epsilon 0, the mass of the electron, and the radius. This we have seen in the classical model. Remember, Bohr said that the classical physics, we can apply it while the electron is rotating in the orbit, but the classical physics, or the laws of classical physics, do not apply when the electron jumps from one state to another state. Okay. Okay. So V squared is equal to E squared over 4 pi epsilon 0 mr. This is from classical treatment, from F equal ma that we just did. And this is also equal to n squared h bar squared m squared r squared from from the quantization condition. Okay. Now, let's take these two equations. These two equations tells us that, well, e squared 4 pi epsilon 0, the mass is equal to n squared h bar squared over m squared r squared. Well, I can easily get rid of the mass here and get rid of one r here also, right? And I can isolate the radius. This will give me the radius is equal. Okay, so you can easily take the radius, and the radius will be equal to n squared 4 pi epsilon 0 h bar squared over m, the mass of the electron, and e squared. What do you see here? This is a constant. This is a constant. Okay, so if you calculate this constant, we call it A0. We call it A0, and A0 is equal to 4 pi epsilon 0 h bar squared over m e squared. So epsilon 0 is constant, the permittivity of free space. This is a Planck's constant divided by 2 pi, it's a constant. This is the mass of the electron, which is constant. This is the charge of the electron, it is constant. So this quantity is constant. So what does this mean? This means that, I don't know why. Yeah. So this means that the radius is equal to n squared times A0. What is this? This means if inside the atom, you have those orbit, and each orbit has a specific radius. So this is, we call it Rn. This means the radius of first orbit is equal to A0. The orbit 2 is equal to 4A0. Orbit 3 is equal to 9A0, and so on. So this will be n equal 1, n equal 2, n equal 3. So this means that quantization of the orbit, If you remember, those are the stationary states where when the electron is there, the electron does not radiate radiation, does not lose energy. Okay, so now the first thing is the quantization of energy. N is called principal quantum number. We'll see it in detail also. Okay, and A0, which is equal to 4 pi epsilon 0 h bar squared over the mass of the electron e squared. This is, if you do this calculation, it will give you a value which is 10 to the minus 10 meters, or 0.553 angstrom. Angstrom is 10 to the minus 1 angstrom is 10 to the minus 10 meters. This is called the Bohr's radius. Okay. So this is called the Bohr's radius. Now let's see what happens to the energy of the system. Now we have seen that the energy of the system is equal to minus e squared over 4 pi epsilon 0 r. Now we can replace r by its value. This gives me minus e squared over 8 pi epsilon 0, and r, let's say r, we know that r is equal to n squared a0. Okay, because if you remember, Rn is equal n squared times E0. So this means that the energy is equal to minus E squared over 8 pi epsilon 0 A0 divided by n squared. This is a constant, which we also call A0 over n squared. So what happens here is that quantization of energy also. Quantization of energy. And if you do the calculation, this E0 is exactly 13.6 electron volt. So this is 13.6 electron volt divided by n squared. This is a quantization of energy. So the question here now, or the conclusion, that based on the assumption, quantization condition of Bohr, we got the exact radius of the orbit and their exact energy. Let's summarize. I have a proton here. This is the first layer. This is the second layer, for example, and this is the third layer. So the first layer, it has n equal 1, it has R1, and it has E1. So what is when n is equal 1? R1 is equal to A0, which is 0.53 10 to the minus 10 meters. And its energy, E1, is equal minus 13.6 electron volt, of course, divided by 1. This is the first layer. The second layer, n equal 2, and now when n equal 2, the second orbit, the radius of the second orbit is equal to 4A0 because it's n squared. So this is equal to 4.53 10 to the minus 10 meters. And the energy of the second orbit is equal to minus 13.6 divided by n squared, which is 4 electron volt. And the same thing, the N3, the radius of N3 will be 9A0, and its energy will be minus 13.6 divided by 9 electron volt, and so on. Okay, so this is N2, this is N3. So now what we got from the Bohr's assumption is a calculation of the radius of the orbit and the energy of the orbit. Okay, now what is interesting is the second assumption. Let's see what is the second assumption. Second assumption is telling us if the electron goes from, let's say, yeah, so let's go to a clean, I will represent, this is the proton, this is n equal 1, this is n equal 2, and this is n equal 3. So here I have R1 E1, R2 E2, and R3 E3. Please follow now because it's become interesting here. Now, the second assumption is the following. When the electron, if we want, let's say the electron is here. If we want the electron to go from a lower state to an upper state, we have to provide energy, and this energy must be equal to the final energy minus the initial energy. We have to provide energy. Now, if the electron, for example, is on upper state and it is jumping to a lower state, then it's the opposite. The energy, the electron or the atom will radiate an energy, a photon, and this photon has again the energy, which is the final minus initial state. So please remember, if you want to move the electron from a lower state to a higher state, you have to provide energy. And this energy must be exactly the difference between the energy of the two states. Now, if the electron moves from or jumps from an upper state to a lower state, the atom will radiate a photon, and this photon again is exactly the difference between the two energies. Please remember this. Now let's give an example. Let's assume I have an electron. I don't know why it became. So electron jumps from n equal 3 to n equal 2. Of course, we are talking from n equal 3 to n equal 2. So this means the electron will radiate a photon, and this photon will be equal. So usually I always take the absolute value. It will be equal to, because the energy of a photon is positive, so it's equal to the energy of level 3 minus the energy of level 2. Now we know that the energy of level 3 is minus 13.6 divided by 9 electron volt. Energy of 2 is minus 13.6 divided by 4 electron volt. Well, this means that these electrons will be minus 13.69 plus 13.6 divided by 4. And you can easily do the calculation. You can do it very quickly here. So this will give you minus 1.511 plus 13.6 plus 3.4, which will give you 1.89 electron. So the photon's energy that is emitted, the photon energy that is emitted when the electron jumps from a third state to a second state is 1.889 electron volt, or you can convert it to joule. Okay. So this is the Bohr's assumption to solve the problem of classical model. Now, what is very interesting, and we will see it later, is the following. In fact, if you remember, we talked about line spectra. If you remember, we talked about line spectra. What are the line spectra? Line spectra is the radiation that we saw, for example, from the hydrogen. If you remember, we had this is the wave length axis, and we saw one line here, 3 lines here, and something here also, if you remember, chapter 3. So those line spectra, what is this? This is a line that corresponds to a transition from one state to another state. This is exactly something like that. And in fact, if you remember, Rydberg made a semi-empirical formula, remember, that is equal to 1 over lambda alpha is equal to the Rydberg constant 1 over n square minus 1 over k square. So this had no theoretical meaning, but just based on the semi-empirical. Now, what is very interesting is this now has been, and we will prove it, has been completely explained by the classical model of Bohr. Sorry, by the atomic model of Bohr. So I will stop here, and next, what we will do, we'll say, okay, this is a semi-empirical. How this is related to the Bohr's model of the hydrogen atom. Okay, so I will prove it next time. But please remember, in summary, that the Bohr's model tells us that the electron can only occupy certain state in space. It cannot be everywhere. It can only occupy certain state, certain orbit. Each orbit has a radius that we can perfectly calculate and an energy that we can perfectly calculate. And if the electron makes a transition from one state to another state, if it goes from a lower state to a higher state, you have to give energy to the electron. It's like when you are climbing a mountain. So you have to get a force to help you. If the electron is moving from an upper state to a lower state, it will radiate a photon. And in both cases, the energy is equal to the difference between the energy of the two states. Okay, so we'll see, we'll continue later. Thank you.